Hello students, this is Ms. Ruiz. Got a video for you today. We're going to be learning about something new. It's called rational and irrational numbers. So basically we're going to be classifying numbers into either being rational numbers or irrational numbers, okay? So please make sure you title your page and write today's date. You want to copy down the notes that I have here, so pause the screen, copy down your notes. And I will scroll up a little bit, pause the screen, copy down your notes, and make sure you copy down the whole page. Here's what it will look like from my page. All right, so let's get started. Okay, so rational and irrational numbers. Well, the good news is we have been working with rational numbers a lot. So you'll recognize rational numbers because they're the numbers we've been working with in class over the last couple of weeks, and also the numbers that you're used to working with since you've been in school. So we've been working on fractions and how we turn fractions to decimal. So the fraction 3/4 will become the decimal 75 hundredths. We've also learned, and that's a terminating decimal, right? 75 hundredths. We've also learned you can take a fraction and turn it to a decimal, and we could get a repeating decimal with the repeating sign over it, okay? So fractions and decimals are things that we've been working with. We've been working with how to take a decimal, 825 thousandths, for example, and turn that into a fraction. So we can take a decimal, any of these decimals, and convert it back into its fraction form. We can take a decimal here and turn it to a fraction. We can take a fraction, turn it to a decimal. We've also been working with square roots and cubed roots. So we know that if we have a perfect square, for example, we're asking what the square root of 121, that's going to be a positive or a negative 11. It's going to go simplify down to a positive and negative integer. The same thing for a cubed root. If we're working with a cubed root, a perfect cube, we know we can simplify it down to a positive integer. We've also worked with some non-perfect squares and non-perfect cubes, like the square root or the cubed root of 2 or 5. Those would be non-perfect, and we've estimated those to the closest whole number and 10. All right, so let's take a look at what is the difference then. How do we classify these rational and irrational numbers? So rational numbers are the numbers you're probably most familiar with. Irrational numbers, it's really what is the new definition. And they're numbers that can't be written as a ratio, or in other words, written as a fraction. And I'm going to start with irrational numbers because really, there's only really two types, but I'm going to classify them as 3 types and make one its own category. And then every other number we've been dealing with is rational numbers. So really, let's take a look at what the irrational numbers are first. So irrational numbers have these attributes, right? They have these 3 attributes here. They cannot be written as a fraction. That's kind of the definition, or a ratio. We can't write them as a fraction or a ratio. So how do we recognize them? Really, the way you want to recognize them is this here. They are non-terminating and non-repeating decimal, both of those things. So basically, that means that it never ends. Okay, that's what non-terminating means. It never ends. And so this number, think about this decimal that's going on forever and ever and ever. It's never ending. But when you look through the numbers, it's non-repeating. So it never repeats. Okay, and that's the difference, because when we're looking at rational numbers, the decimals will either end, and we know that to be a terminating decimal, or it'll go on forever, but it has a repeating block. Some numbers that actually just repeat forever and ever. So if it doesn't do either of those 2 things, it has to be an irrational number. Okay, when you look at it, it won't have any logic to it. It's just random numbers going on forever. making no sense. Okay, so non-terminating, non-repeating decimals would be irrational numbers. And also those non-perfect squares and non-perfect cubes we've been working with. So they don't numbers that do not come from an integer. These non-perfect squares and non-perfect cubes we've worked with a lot in class, and those would be irrational numbers. So basically, if you see any non-terminating, non-repeating decimals, or any non-perfect cubes or squares. Now, I did say there were 3 types, and those are really 2. The third one is a non-terminating, non-repeating decimal that is known as pi. Okay, so we're going to talk about that a little bit more. So anytime you see pi, pi is a decimal that never ends. It goes on forever and ever and ever. It's never ends. But it also doesn't repeat. And it's an actual value that we use often in mathematics so that it has its own name called pi. But any other decimal that also does not terminate or repeat is also an irrational number. Okay. Now, what about rational numbers? Well, these are the ones we've been working with. They're numbers that can be written as ratios or as a fraction. Well, we've been working with fractions. So if you see a fraction, it's a rational number. If you have any number and you can turn it into a fraction, like an integer, you can turn it into a fraction by putting 1 under it as the denominator. Any decimal that we can turn into a fraction, so that brings us down here, our terminating and repeating decimals. Well, we've learned how to turn those into fractions. And if I take any perfect square or perfect cube, well, those are going to simplify to an integer. And that integer can be turned into a fraction, like I said up here, by just putting a 1 as our denominator. So most of the numbers you've worked with in your life and in this class are rational numbers. Let's take a look at some examples of both of them. So we'll start here on this side with the rational number examples. So any integer, we have the integer here 6. And a way to explain or to prove that it is a rational number, if I can turn it into a fraction or a ratio, well, just putting the denominator of 1 turns that into a fraction. Same thing with -3. If I just put a 1 as the denominator, I have a fraction. I can also write that as a decimal, right? The number 6, you can think about it as 6.0. It also can be written as a decimal, a terminating decimal. Fractions, well, if it's already written as a fraction like 3/4 or -1 1/4, these are fractions. It doesn't matter if they're positive or negative. These would be considered rational numbers. Terminating decimals, well, we know that we could take, for example, 3/4 and it will become 0.75 hundredths. We can turn that into a terminating decimal, or I can take a fraction and turn it into a repeating decimal. So terminating and repeating decimals that you're already familiar with, those are rational numbers. So you've been working with these numbers. The square root of 16. Well, we know the square root of 16 is going to simplify down to 4, a positive or a -4, right? So positive or -4, both of those can be turned into a fraction. So the square root of 16 equals a positive or a -4, and that is a rational number. The cubed root of 8 we know equals a +2, and we can turn 2 into a rational number putting a 1 under it. So most of the numbers that you have been working with in your life and in this class are going to be classified as rational numbers because there's some form or way to turn them into a ratio or a fraction. So that makes it a lot easier to find irrational numbers. You can kind of test everything to see, well, is it irrational? Does it fall into one of these 2 categories? And if not, everything else would be rational. So for instance, here we have this decimal. It's 0.137856. And these dots tell me that it goes on forever. But if I look at it, there's no repeating bar on top. It doesn't have any numbers that repeat. It just goes on forever with random numbers. That tells me it's kind of hard to wrap your mind around that. It never ends and it never has any pattern. It's just willy-nilly numbers all over the place. Well, that is irrational. It never ends and never repeats. A non-repeating, non-terminating decimal is an irrational number. Pi is one of these numbers. So in class, we're going to take a look at pi together, and we often estimate it or approximate it as 3.14 when we're using it in calculations. But it really never ends. It has those three dots, the ellipses that tells us it goes on forever. It never ends. But it also doesn't have any repeating blocks. So pi, or any problems you see with pi being attached to them, are going to make that an irrational number. So if you see that it has non-repeating, non-terminating decimal, also including pi, it's irrational. These two indicators would be irrational. And then the other thing you want to look for, well, if it's being presented as a square root, take a look to see if the square root is a perfect square or a non-perfect square. So we know that the square root of 2, and I'll do the example here, we know that the square root of 2 from what we've done in class, the square root of 2, well, there's not going to be one number times itself that's going to give me the square root of 2, but I know that that will be between the perfect square of 1 and the perfect square of 4. 1 squared comes from, square root of 1 comes from 1 squared, and the square root of 4 comes from 2 squared. So we know it'll be between 1 and 2, but it's not coming from an integer. That tells us it's a non-perfect square. And we've done these in class together. So non-perfect squares and non-perfect cube roots would also be considered irrational numbers. Everything else that we've dealt with will be considered a rational number. So in this section, we're going to have to be able to recognize and classify a number and say if it's rational, irrational. We'll do a few now, and then we'll practice this some more in class. So let's take, for example, so here we have some examples, and we're going to take the value here, and we're going to decide if it's rational or irrational. And we're going to give an explanation as to why. Okay. So if I take the number negative 15, I'm going to have to classify negative 15 and decide whether it is rational or irrational. Well, let's think about it. Can I turn negative 15 into a fraction? Yes, by making that 15 over 1. I can turn that in, or negative 15 over 1. That becomes a fraction, so that makes it rational. Okay. Why? Because it can be written as a fraction or a ratio. Okay. And I like to use the word ratio sometimes because ratio is in the word rational. If you remember that ratio and fractions are the same thing, then you'll remember that anything that is a fraction or can be turned into a fraction is a rational number. All right, let's take a look at another one. If I show you the example of 4 pi, well, 4 is a rational number. I can turn that into a fraction. But if I multiply 4 times pi, which is an irrational number, I am going to get an irrational number. Okay? And we know that pi is irrational because it is a non-terminating and non-repeating number. Okay? So if it is non-terminating and non-repeating, both of those things, it is irrational. All right, let's try a couple more. So if I were to show you the number 0.25 or 25 hundredths, We know that 25 hundredths is a decimal that ends here at the 5, so it's a terminating decimal, and that would make that a rational number, and it is rational because it's a terminating decimal. We can also say it's rational because it can be turned to a fraction. We practice these in class. You turn this into a fraction, it ends in the hundredths place. You write it as 25 over 100. At that point, it is a fraction, and then we can simplify it. But it can be written as a fraction. That makes it a rational number. Okay, so another example we could use here would be the square root of 7. So if I'm using the square root of 7, I can ask myself, well, is there a number times itself that will give me 7? And so I can look at my list or think about my perfect squares or my integers as I multiply them. And 7 is not going to be a perfect square. So because of that, it's going to be irrational. I can estimate where it would be, but that's going to be a non-perfect square. And so that's the reason. It is a non-perfect square. Okay. I'm going to give you 2 more for you to try on your own, and we will go over these together in class. So why don't you tell me if this number would be considered rational or irrational, and tell me why. We'll talk about that in class. And this number let me know if you think this number, -3 and 75 hundredths, is considered rational or irrational, and tell me why. We'll talk about those in class when I see you next time. Take care.